I'm going to do the 2018 AP Chemistry FRQ question number 6. And you can see this has to do with a little bit of electrochemistry. So it says that a student sets up a galvanic cell at 298 Kelvin, which is standard, that has an electrode of silver in a 1 molar solution of silver ions and chromium in a 1 molar solution of chromium ions. So that is a very standard cell. The student measures the voltage of the cell and discovers that it's 0, so identify the missing component and explain its importance for obtaining a non-zero voltage. So the idea here is we are missing the salt bridge, which can take various forms, but classically it's a glass tube stuffed with cotton in the ends, and it contains some kind of a solution of ions, something that will not mess up the reactions. So a couple of spectator ions like potassium nitrate is a classic thing to use. So we would have a salt bridge. Now, so the salt bridge is what we're missing. And why is it so important? Because what it does, it allows ions to flow from one cell to the other, because you want to keep these two cells electrically neutral. So this is a conduit for the ions to go through. One thing that people said that got them in trouble was about electrons. If you even mentioned electrons, you were in kind of trouble unless you were talking about the fact that the electrons were moving through the outer wire. Maybe a little picture would be okay. So if you did mention electrons, you had to make sure that you were not implying at all that they were going through the salt bridge. Salt bridge is for ions. Now the next part here is saying, well, here's silver. Okay, here's the half reactions for this, and we're given the number for silver being reduced, and here's chromium that could be reduced. And the student adds the missing component to the cell and measures the voltage to be positive 1.54 volts. As the cell operates, silver ions are reduced. So that's important. So we know this is reduction, and that means that this reaction is occurring as written, which means this reaction is going to have to happen in reverse. So calculate the E0 for the half reaction here. We want to calculate that value. So for part I, okay, one thing I know is that the E of the cell is equal to the oxidation potential plus the reduction potential. Now, what do we already know? The E of the cell is negative 1.54 volts, because we were told, I'm sorry, positive 1.54 volts. Oops, that was a big mistake. And we want to know this oxidation potential, and we know that the reduction potential is positive 0.80 volts, because we said the silver is being reduced. So we have to solve for X, so we can see what's going to happen. Subtract 0.80 from both sides, and we're going to get positive 0.74 volts. But that's the oxidation potential, and they want the reduction potential, so we have to turn the sign around. So the answer that they're asking for is the reduction potential of chromium, and that is going to be negative 0.74 volts. So here's our equation. We knew the reduction potential because that was silver. We knew the E of the cell. We figured out the oxidation potential, which is this number in reverse. So we changed the sign and we got our point. So that's 1 point so far. Next it says, write the balanced net ionic equation for the overall reaction that occurs as the cell operates. Well, that's pretty easy. So if we go here, we can see back here in the equation that silver ions are turning into silver metal, getting reduced, and that the chromium is not happening in this direction, it's happening in reverse. So chromium metal, okay, is turning into chromium ions plus 3 electrons. We're going to combine those two, and the electrons have to cancel out, so we need 3 on everything on this top part. So the electrons cancel. So our final answer here is going to be 3 silver ions plus chromium, turns into a chromium ion, and 3 silver neutral. And that gets us our second point. for part II. I'm sorry, that was the third point. So we got 1 point for talking about the salt bridge, second point for calculating the reduction potential for chromium, and the third point for writing the overall equation. Okay, the next part here is part III. Okay, and that says calculate the delta G for the overall cell reaction. So if we look up on the chart in the equations, we find out that there is a reaction that connects delta G with the F, okay, with the E0 value. So delta G equals negative N F E0. And the big idea here is in 3 different chapters we get ideas that tell us whether a reaction is going to be product favored, where it's going to go. Delta G is one of those, and a negative delta G means we have a nice thermodynamically favorable reaction. E0 is one that tells us also if we get a positive voltage, then we know that we have a nice reaction that's going to go. And the other one is the KEQ. And if we have a KEQ that's larger than 1, that is going to say that's product favored. So there are equations on the equation sheet that let us link these things, and we can go back and forth between, and we're asking to go back for these two right now. So negative NFE. So the delta G, okay, equals negative. N is the number of moles of electrons that were transferred in this reaction. And what we just said, we canceled out 3 moles of electrons. So we have 3 moles of electrons for every 1 mole of reaction. 3 moles of electrons for every 1 mole of reaction. That's the value of N. Okay, Faraday, that is a constant, and we get that from the chart, and it's 96,485. And that's coulombs, which is the amount of charge per mole of electrons. And the last thing here is the 1.54 volts. But it also says in the chart that a volt is the same thing as a joule per coulomb. And that's an important little idea here because we need to use joules over coulombs to make all of other units cancel out. So the coulombs cancel out. Okay, we have moles of electrons and moles of electrons. And we can see what we have here is we have joules per mole of reaction. And so we just have to calculate. So negative 3 times 96,485 times 1.54. And we end up with a number 4.46. And that's a negative, don't lose our negative, times 10 to the negative 5. And that's joules per mole of reaction. Okay, I'm going to write that again because that's really messy. So negative 4.46 times 10 to the negative 5 joules per mole of reaction. And if we made it this far, then we just earned our 4th point. So this kind of question here is very easy. Watch out for the N. Okay, you're going to need to get the N from the balanced equation, how many electrons you cancel out. And notice that that's mole of electrons per mole of reaction. That's where the mole of reaction comes in. Okay, here's our constant, Faraday constant. And again, we have to do something funny with our units, change our volts into joules per coulomb in order to make that all work out. And that is question number 6.